center of the largest planet. The electrical current in the liquid metallic interior of Jupiter may be the source of the planet's enormous magnetic field, the largest in the solar system, and of its associated belt, the trapped electrons and protons. These charged particles are ejected from the Sun in the solar wind and captured and accelerated by Jupiter's magnetic field. Vast number of them are trapped far over the clouds and are condensed by bounce from pole to pole until by chance they encounter some high altitude atmospheric molecules and are removed from the radiation belt. EO moved in an orbit so close to Jupiter that they plows through the midst of this intense radiation, creating cascades of charged particles, which in turn generate violent bursts of radio energy. They may also influence eruptive process on the surface of Io. It's possible to predict radio bursts from Jupiter with better reliability than the weather forecast on Earth by computing the position of Io. So Jupiter is a source of radio emission discovered accidentally in the 1950s, the early days of radio astronomy. Two young Americans, Bernard Bach and Kenneth Franklin, were examining the sky with a newly constructed and for that time very sensitive radio telescope. They were searching the cosmic radio background, that's radio source far beyond our solar system. To their surprise, they found the intense and previously unreported source that seemed to correspond to no prominent star, nebula, or galaxy. What's more, as it gradually moved with respect to the distant stars, much faster than any remote object could. After finding no likely explanation of all this in their chart of the distant cosmos, they one day stepped outside the observatory and looked up the sky with the naked eye to see if anything interesting happened to be there. Bemusedly, they noted an exceptionally bright object in the right place, which they soon identified as the planet Jupiter. This accidental discovery is incidentally entirely typical of history of science. Every evening before Voyager's once encountered Jupiter, I could see the giant planet twinkle in the sky, a sight our ancestors have enjoyed and wondered as for a million years. As on the evening of encounter, on my way to study Voyager data arrived at JPL, I saw the Jupiter would never be the same, never again just a point of light in the night sky, but the world forever after be a place to be explored and known. Jupiter and its moons are a kind of miniature solar system, and executive world is much to teach us. In composition and in many other respects, Saturn is similar to Jupiter. Although smaller, rotating once every 10 hours, exhibits colorful equatorial banding, which is, however, not so prominent as Jupiter. It has a weaker magnetic field and radiation belt than Jupiter, and a more spectacular set of circumplanetary rings, and it's also surrounded by a dozen more satellites. The more interesting of the moons of Saturn seem to be Titan, a large moon in the solar system, and the only one with a substantial atmosphere. Prior to the encounter of Voyager 1 with Titan in November 1980s, our information about Titan was scanning and tantalizing. The only gas known unambiguously to be present was methane, CH4, discovered by G.P. Kupier. Ultraviolet light from the sun converts methane to more complex hydrocarbon molecules and hydrogen gas. Hydrocarbon should remain of titan, covering the surface with brownish, tarry organic sludge, something like the produced in experiment on the origin of life on Mars. The lightweight hydrogen gas should, because of Titan low gravity, rapidly escape to space by a violent process known as blow-up, which should carry the methane and other atmospheric constituents within. But Titan has an atmospheric pressure at least as great as that of the planet Mars. Blow-up does not seem to be happening. Perhaps there is some major and yet undiscovered atmospheric constituent, nitrogen, for example, which keep the average molecular weight of the atmosphere high and prevent blow-up. Perhaps blow-up is happening, but the gas lost space are being replenished by others released from the satellite interior. The bulk density of Titan is so low that there must be a vast supply of the water and other ice, probably including methane, which at unknown rate being released to the surface by internal heating. When he examined Titan through the telescope was a barely perceptible reddish disk. Some observers they reported visible white cloud over the disk, most likely clouds of methane crystal. What's responsible for the reddish coloration? Most students of Titan agree that the complex organic molecules are the most likely explanation. The surface temperature and the atmospheric thickness are still under debate. There have been some hints of enhanced surface temperature due to atmospheric greenhouse effect. With abundant organic molecules on its surface, on its atmosphere, Titan is a remarkable and unique denizen of the solar system. The history of our past voyage of discovery suggests that Voyager and other spacecraft reconnaissance mission will revolutionize our knowledge of this place. Through the break of the clouds of Titan, you might glimpse Saturn and its rings, their pale yellow color diffused by the intervening atmosphere. Because the Saturn system is 10 times farther from the Sun than is the Earth. As the sunshine of Titan is only 1% of the intense as you are accustomed to. The temperature should be far below the freezing point of water, even with the sizable atmospheric greenhouse effect. But the abundance of organic matter, sunlight, and perhaps volcanic hotspots, the possibility of life of Titan cannot be readily dismissed. In the very different environment, it would, of course, have to be very differential from life on Earth. There is no strong evidence either for or against life of the Titan. It's merely possible. We are unlikely to determine the answer to this question without the landing instrumental space vehicle on the Titan surface. To examine the individual particles composing the ring of the Saturn, we must approach them closely, for the particles are small snowballs and ice chips and tiny tumbling bonsai galaxy or a meter or so across. They are composed of water ice because of spectral properties of sunlight reflected off the rings match those of ice in the laboratory measurement. To approach the particles in a space vehicle, we must slow down so that we move along with them as they circle Saturn at some 45,000 miles per hour. That we must be the orbit around Saturn ourselves, moving at the same speed as the particles. Only then we'll be able to see them individually and not as smears or streaks. Why is there not a single large satellite instead of a ring system around Saturn? The closer a ring particle is to Saturn, the faster its orbital speed, the faster its falling around the planet Kepler's third law. The inner particles are streaming past the outer ones. The passing line, as you see it, is always the left, although the whole assemblage is tearing around the planet itself at some 20 kilometers per second. The relative speed of two adjacent particles are very slow, only some few centimeters per minute. Because of this relative motion, the particles can never stick together by their mutual gravity. As soon as they try, their slightly different orbital speed pull down apart. In the ring, if the ring were not so close to Saturn, this effect would not be so strong, and the particles could accrete, making small snowballs, eventually growing into satellite. So it's probably no coincidence that outside the ring of Saturn there is a system of satellites varying in size from a few hundred kilometers across the Titan, a giant moon nearby as large as the planet Mars. The matter in all the satellites and planets themselves may have been originally distributed in form of rings, which condensed and accumulated to form the present moons and planets. For Saturn, for the Jupiter, the magnetic field captures and accelerates the charged particle of solar winds. When a charged particle bounces from one magnetic pole to the other, it must cross the equatorial plane of Saturn. If there is a ring particle in the way, the proton or electron is absorbed by this small snowball. As a result, for both planets, the rings clear out the radiation belt, which exists only interior and exterior to the particle rings. Close moons of Jupiter or Saturn will likewise gobble up the radiation belt particles. In fact, one of the new moons of Saturn was discovered in just this way. Pioneer 11 found an unexpected gap in the radiation belt, caused by the sweeping of the charged particles by a previously unknown moon. The solar wind trickled into the outer solar system far beyond the orbit Saturn. When Voyager reached Uranus and the orbit Neptune or Pluto, if the instruments are still functioning, they will almost certainly sense its presence. The wind between the world, the top of the sun's atmospheric balloon, outward toward the realm of the stars, some 2 or 3 times farther from the sun than Pluto is. The pressure of the interstellar protons and electrons becomes greater than the minuscule pressure they are exerted by the solar wind. That place, called the helioforce, is one definition of the outer boundary of the interior of the sun. But the Voyager spacecraft will plunge on, penetrating the helioforce sometime in the middle of the 21st century, skimming through the ocean of space, never to enter another solar system, destined to wander through eternity far from the stellar island and complete its first circumnavigation of the massive center of the Milky Way a few 100 million years from now. We have embarked on epic voyages.